The objective here is to explain what we're working on. So someone's going to turn off the lights. Of course, we need to be in a dark space in order to see the black hole, because the black hole is black. And to see it in the black of space is difficult, right? How do you see something that's black? And the answer is that, fortunately, this is an active black hole in M87, where things are still falling in on top of the black hole. And it is the stuff which falls around the black hole which radiates very brightly. And what we are seeing here is the last bit of light before the light itself is sucked into the black hole. So this is the characteristic signature, we think, for a black hole, which is a ring of light. So I need to just, for those of you who are not astronomers, to explain why we use so much money in astronomy. And the reason is that, of course, astronomy is the oldest field everywhere, right? We've been doing this for a long time. And the fundamental question that we address is existence itself. Why are we here? And astronomy studies the biggest space, right? We study the entire universe, from here to the edge of the universe. And we study all time, from the beginning, at the beginning of the universe, into the future, where we extrapolate what will happen in the universe, right? So, biggest space, all time. This is our field. That's why we need big budgets, more than anybody else, right? And we answer these questions about origins. And these things are easily appreciated by the public, which is why we think it's also a very good way to stimulate support for science, which is the answers for the future, okay? And of course, our field also drives technology developments and transfer into the public sector. And we are, of course, driving the big data science, which is so popular these days in the discussions. So I'll just quickly summarize the talk in case you fall asleep. Here's the things that I want you to go away with. One, black hole imaging is one of 3 key gravity experiments that we have today. And Asia plays a strong role in this last experiment, which is on the black hole. And the common techniques in these studies is lasers and interferometry, which I'll explain. And then the black hole shadow itself, of course, verifies general relativity and provides deep implication for many things that we want to understand in physics, astrophysics, and fundamental physics. And we are working on this very important next steps. And the last message, which is that in order to do these things here, elsewhere, in order to do the very high level excellent science, we actually require government support, working together with the research organization, the industries, and the universities together. That's how we make it possible. So in 2019, we showed the first image of the supermassive black hole. It was a very popular story. It was on all the newspapers. Now, how do you know you have a good result? Is if you get on the Google banner, right? If you're on the banner, you know this is something really important. And the banner actually was made up by this guy driving to work that morning. And he captures everything that is necessary, right? Namely, there's a black hole, it sucks everything in, all gone. So this result actually had already won many important prizes, including the Breakthrough Prize in Fundamental Physics, and also on the right, I know very proudly for Taiwan, the CTCI award was given to our team for working on this particular problem. So why are black holes important? They are, of course, we say, key to the fundamental physics. First time we see things that are invisible or thought to be not seeable. This is very exciting. You know, if somebody tells you this thing just can't be seen, and now we can see it, that's very exciting, right? Also, this is where gravity is strongest, as far as we can tell, at the edge of the black hole. No escape, light itself is sucked in, no information come out. It's a very mysterious topic. Now, for small black holes, we've known for a long time, this is the end state of stars, right? If a star is bigger than 5 times that size of the sun, the end state, when it burns all the nuclear energy, when all the energy is exhausted, you get a bounce in the collapse, that's the supernova. The core that remains will continue to contract down into a singularity. We know these, we've seen these in X-rays. The big black holes, which are billions the size of the sun's mass, billion times, they are in the nucleus of galaxies. We actually believe that every galaxy probably have a very big black hole in the middle. How they are made, we don't know, okay? But how do we understand black hole? the properties are the density, the temperature, and I will tell you that it depends on the size of the black hole. Okay? So the physics, of course, is very important because these are extremely good cases for testing general relativity. And the experiments that we're talking about in this field, in this gravity field, is all about missing information. Okay? So in effect, it's an optics problem where you have distortions, missing information. How do we recover? So physics are very simple. Things like escape velocity, everybody knows how to do this in Newtonian mechanics, balancing the kinetic energy and the gravity. And if you do this calculation, square root of gm over r, you'll find that the escape velocity on Earth is about 11 kilometers per second. Not very large, okay? But if you get that, you can escape from the Earth's gravity. And for the solar system, it all goes about like that on that order, with Jupiter being the biggest, about 60 kilometers per second, okay, for escape velocity. So how do you know when you cannot escape from a black hole? It comes from this Schwarzschild radius, okay? Basically, it's because the speed of light cannot be exceeded. So in that equation, where the escape velocity is limited by the speed of light, now you have a limit on this Schwarzschild radius where you do not have enough energy to escape, okay? In other words, given the amount of mass, if the size is small enough, then the gravity is too strong that you cannot escape, okay? And that's just a Newtonian calculation, right? But if you go through general relativity, correctly calculating, you'll get just the same answer. So this effect comes from special relativity, which actually tells you that the energy becomes infinite if you want to escape beyond the speed of light, and that's embodied in that equation, famous equation E equals mc squared, where you have correction factor gamma, which blows up as you approach the velocity of light. In general relativity, then tells us that even light will follow the distortion due to gravity, okay? And the metric of the black hole is defined by that ratio, m over r, right? The mass, the amount of mass you can pack into a certain size scale. And then, how do you know what is the physics inside the black hole? Well, the interesting thing is that the metric, as I say, is mass over size, but density is mass over r cubed. So now you see, depending on the mass, depending on the size of the black hole, the density can actually be very unusual, like an Earth-sized black hole. The density will be 10 to the 27 times that of water, but in the M87 black hole, the density is only 10 to the minus 3 that of water. And in fact, if you calculate the universe and calculate the total mass and total size, it's on the order of what you might need for a black hole. So in other words, the universe itself could be a black hole. Then what is it inside this particular black hole is actually quite normal, right? It's just what we are. Why is that? Because the density describing that black hole is actually quite low, right? If you're on the universe. So quickly, what does the image actually say? It's black, looks like a hole. That's the answer, black hole. Okay? Size scale, the actual physical size scale is about the size of the solar system. Okay? We'll come back and talk about this. Other simple physics that you will need in order to do this are actually rather simple. Things like light, energy is proportional to temperature, right? So scales with the frequency of the light, scales with the wavelength. The shorter the wavelength, the more energetic it is. Speed of light is a constant. The size of the thing that you see depends on the distance. The things that are further will look smaller. Total energy is, of course, conserved. Angular momentum is conserved. Things like Doppler motions need to be understood. And that is actually quite simple. This is the usual effect. Things that are approaching you will have a higher frequency. Things that are receding from you has a lower frequency because the wavelength has been stretched out, right? This is the usual train whistle coming towards you and away from you. The pitch is different. And that effect is what we call Doppler boosting. You will make one side, which is approaching you, versus the other side, which is receding from you, to be different in intensity of light. Okay? So, light itself, of course, the eye only see a very small fraction of the electromagnetic spectrum, right? That's because our eyes are tuned to the sun. We respond to the sunlight, which is at 6,000 degrees. The rest of the universe is actually quite cold. The universe itself is only on the order of a few degrees, right? Because it's empty. And that low temperature actually peaks around submillimeter wavelength. And that is the reason why we're working in this experiment in submillimeter wavelengths. We developed the technology there where we can build very large structures and we can maintain the sensitivity to see that signature at that cool temperature, okay? The experiment is to balance the resolution that we can do versus the energy that we can actually receive. So that's a very delicate balance in choosing the experiment. Okay, so now let me go back and talk about black hole research. In black hole research, there's 3 types of experiments that we can think about. One is to hear it, one is to feel it, and one is to see it, okay? Hearing it is actually the detection of gravitational waves. Now there are tens of cases, more every day, okay? And feeling it is actually the orbital motion of a test particle around the gravitational field, right? And there's one case, which is the galactic center. And then there's the seeing it, or not seeing it, which is the imaging of the event horizon, of which there are 2 cases. And all of these experiments, of course, explore the general relativity effect. As I mentioned, is lasers and interferometry. That's the key technique that we do in this field. And you can ask, are these Nobel Prize winning work? And the answer is yes. 2 of them, the first 2, hearing and feeling, have already won the Nobel Prize. So, of course, the question that was put to me is to explain what kind of research is Nobel Prize level, right? And of course, one of the answers is that you have to be very lucky. The second answer is that you have to work very hard. And the third answer is that it takes a whole long time in order to get there. So the first experiment to explain to you is hearing, which of course, Wei Xing has already shown you. This is hearing the gravitational wave. And these are basically interferometer experiments. Various sites, a long vacuum tube going for kilometers, evacuated, a light is sent from one end to the other, to measure the separation of that mirror, okay? And that is an interferometer experiment. This is a layout that you could have a benchtop experiment if you like, but except in this case, 2 test particles, 2 test masses are actually separated by 4 kilometers, right? You have to shine a light down that tube, hit the mirror on the other side, and get back over that 4-kilometer sense where the mirror has actually moved or not. Okay? So it's a very delicate experiment in this interferometer mode to test the signal. Of course, you can imagine, right? Walking past those mirrors will introduce a strain. A truck rolling by will introduce a strain. All sorts of things will give you a false signal. And the question is, how would you ever detect the right signal? Well, the first thing that we do is called anti-coincidence, is that you insist that the signal has to be detected in more than one case at the same time, right? So a truck rolling by California will not be heard and felt all the way across the world on the other side. And the signal strength, of course, definitely will not be the same, right? So you're looking for that coincidence over the several interferometers that we have in place, okay? And the second thing, of course, is that what you hear is this ringing, right? On this plot, on the top plot is signal to noise, and the central row is the frequency of the signal. The lowest row is actually the strain that you're measuring. And you see this characteristic signature, a slow rolling thing coming in, it gets a little bit more excited, and then it fades, right? And the sound, we call this hearing, because the frequency that you actually see is on the order of about 100 hertz, which we can show you in his talk. That is the sound that our ear is sensitive to. That's why we call it hearing, okay? And that signature, you can say, only lasts about 1/10 of a second, and it only comes once, right? Because this is a collapsed signature of 2 very large, massive bodies. How would you know 1/10 of a second, sometime, anytime, coming through is actually your signal? And the answer is, you have to have good theory in place. The theoretical calculation already predicted what that little wiggling signal would be if 2 massive objects are colliding, how that gravitational wave should come through in that ringing pattern, at the frequency and the structure. So now we have many cases. These are just a handful of them. You can see the same signature, a rise in the signal, ringing, and then fades, okay? So the in spiral and the expiring signal. Now, the question is, once you detect that, you have to say, where is that source? With only 2 or 3 detectors, triangulation is actually quite poor. You can look at the sky in this particular case along the Milky Way. They have a very large area circle that has been established as to where that source can be. It's actually very large because you only have 2 or 3 instruments, so pointing toward the signal is not that accurate. Okay. So how do we do this? We do this is that we actually try to detect that signal. Where is that source? Okay. And this particular picture is to show you that in Taiwan we were already working on this instrument, which is a very large camera, which has been built for wide field imaging on top of the Subaru telescope on Mauna Kea. This is Japan's national telescope, and we participated in building this camera. And with this camera, you can see a very large field of view. You can see the entire Andromeda galaxy at once. Okay, so with this, we were able to, of course, the background is that this experiment actually is meant to do weak lensing. Okay, and you can see some arcs over here on this picture. And this weak lensing actually is from Hubble, shows that the weak lensing is actually measuring something, which is a lens, against the background. And that distortion of the image from the background allows us to measure the dark matter property, because the distortion, the disruptor cannot actually be seen in the visual way. You cannot see it. What is missing is actually the dark matter. This is a different talk, of course, but this telescope will be able to map dark matter distribution along this 3 axis on the sky, as well as the redshift. But with this experiment, with this telescope, we can now swatch a large swath of angle at once, and he detected a very faint source, which then faded on a time scale of a few days. Okay? Now, just seeing a faint source that faded away, who knows what that is, right? To really believe that this is the driver, actually, again, depends on theory. Here we calculate the theoretical prediction for what those decay in signal will be in terms of time after the gravitational wave events, measuring the optical as well as the near-infrared curves actually can fit this so-called event, which they call a kilonova. Okay, and it is through these kind of complementary studies of the light which is coming out, fading away, and yet we're measuring its properties, that allows us to identify as possible sources. So what is the story here is that, going forward, we would like to identify further sources of gravitational wave, find their precursors. We are building larger and larger instruments in order to be sensitive to these gravitational wave events. The reason we would like to be able to track the fading part of the signal in the gravitational wave. There's a lot of signature of the gravitational general relativity effects, second order effects will be embedded in how the light fades. And people are studying this very hard right now, which we think will gain when we have more signal to noise. And also, the current ones are actually rather small events, things like the neutron star colliding with a black hole on a stellar mass type black hole. So the signal actually is very short, tenths of a second, but we are hoping that we'll eventually be able to catch supermassive black holes, binaries that are colliding. In those cases, the in-spiral phase and the post-merger phase will be longer, and we'll be able to do better tests. So these Nobel Prizes, actually in gravitational wave, was given twice already. The first one was actually to Joe Taylor, House, the student, in 1993. They discovered the spin down of the binary pulsars, where the radiation coming out in the gravitational wave accounts for the fact that the period of that binary is slowly decaying. Okay, this was a beautiful experiment for which they were awarded the Nobel Prize. I was a postdoc at the time. Joe Taylor was an assistant professor at UMass, and quickly Princeton hired him away because Princeton could tell also that that was an important experiment. This last one, on the actual detection of the gravitational wave itself, have 3 people: Ray Wise, Kip Thorne, and Barry Barish. Ray Wise actually was the experimentalist, Kip was the theoretician. And Ray, here it is, working in the 1970s at MIT, working on this duo, which is the same kind of duo that we use today. At that moment, he was working on cosmic wave background. 70s to today, 50 years to gain this recognition for this very important piece of work. So what is the backstory of this? I tell you the backstory in order to tell you how things takes a long time, right? So 1917 was when Einstein first published on the quantum theory. And in 1953, Charlie Towns discovered the maser, followed by the laser, for which he actually obtained the Nobel Prize. Okay? Because of that laser, people began to realize that we have a very important tool. Okay, so in the 60s, MIT laboratories were using lasers and trying the best to work on lasers. I myself was a freshman at MIT. My advisor says to me, you should come to evening seminar, right? Sometimes your advisor will tell you also, you should come to evening seminar. I said, I have many classes, I got too much work to do, why should I come to an evening seminar? And my freshman advisor says, we have donuts. I said, donuts? Okay, I'm there. So I went. At this seminar, we worked on what is the most important physics experiments to do. Okay? From that seminar, I began to work on dye lasers to try to build a dye laser that's a tunable laser. It was not very successful. It took me a long time, never got very far. But in there was this assistant professor, Ray Weiss, working away. I remember we studied the Feynman lectures very carefully, trying to sort out what should be the experiment. Okay? And from there is where Ray came with the idea of the gravitational wave experiment. Okay? Took 50 years. Well, I gave up laboratory physics. I thought it was too difficult to do, no future in this. I thought I should do astronomy where I can get some more data, right? So, missed the boat on this particular experiment, even though I have many very nice donuts. Now, the next experiment is gravity can be felt. So, Wei Jing already showed you this movie very quickly. This is about detection of a star which is going around the galactic center. It has a very tight orbit, elliptical orbit that takes about 15 years. And over 20 years, they have been very careful to be able to measure this orbit. And in particular, what's interesting is that in a very popular curve, they already knew there's something very important. They can detect the elliptical orbit. They can see that it will close within a certain amount of time. They can predict how much mass is in the middle, pulling that in. Okay? For this group actually got the Nobel Prize. Today, this experiment is even more complicated. They're using the very large telescope interferometer in European Southern Observatory. Astronomers are not very imaginative. Okay? When you build a telescope, they'll say the telescope. And then you build a bigger telescope, they'll say the large telescope. If you build an even bigger one, they'll say very large telescope. And if you build even bigger than that, they'll say extremely large telescope. And that's how we named them. In this case, it's a very large telescope interferometer, 8-meter telescopes in Chile, working together as an interferometer. And actually, very importantly, it actually measures very careful experiment. The laser shining artificial light source that Wei Jing show you is actually how we do it. But in this case, they actually guide it on a star, nearby star, in order to sharpen the image, right? The adaptive optics closing on that star. And also another star nearby called fringe tracking. That's where we're checking that the interferometer itself is working properly and is actually phasing properly. And with this very careful experiment, they can actually remove the atmosphere, they can track and correct for the interferometer baseline, achieve a very high angular resolution, 3 milliarcsecond with a resolution, relative resolution of 40 microarcsecond, okay? Now, to remember, a good telescope today may be a few tenths of an arcsecond. So this is orders of magnitude better, in order to get to that resolution, to see what's going on, right? So this very delicate experiment can also be seen as a laboratory experiment on a benchtop. In fact, all of these things are in the dome of the observatory, and it is just combining the lasers, correcting for the individual errors in the laser paths, and we do this with lasers and very accurate interferometers. So what is measured? Measured is a very accurate orbital motion with a period of about 15 years. The size scale, you can see the tick marks over here is 5/500th of an arcsecond. 5/100th of an arcsecond, the big ticks here. And then over here on the very tight part, we will see it actually can measure very accurately. With the size scale here about 40 times the solar nebula size. And then on top, you can actually see that we can also measure the velocity by watching the star. We can actually see its rotation in that orbit. Okay? And these are the information for us to deduce the mass in the middle, this type of experiment. And you can see that on a closest approach to the black hole over there. These sources are now moving at 8,000 kilometers per second, much faster than the escape velocity from Earth. and you can see the motion on everyday tracking in this system. So it's a very accurate and very precise measurement, right? And in fact, the motions can be very precise, and you can see that as it gets close to the black hole, actually we see a second order velocity displacement, which is driven by the second order effect in GR. So, future direction. Next generation, we again intend to build bigger telescopes, such as 30-meter telescope, the extremely large telescope that Taiwan is also working on, and we'll get more accurate measurement of the orbit, and then fainter targets. We'll be able to see things that are much fainter, and therefore maybe even see better orbital motions to come. What is the backstory? Say the Nobel Prize was given to 3 people: Roger Penrose, who's the theoretician; Reinhard Genzel, which is on the MPI, and Andrea Ghez is actually at UCLA. And here you can see that Reinhard is working with Charlie Towns, the inventor of lasers. And there's Reinhard, Fredo, and I in our younger days, before we knew something really big was coming. So what's the backstory? Again, Charlie Towns had invented the laser. He was then at MIT, and now he moves to Berkeley from MIT. And you can say, why did he move from Berkeley to Berkeley? Actually, Charlie Towns wanted to be president of MIT. They didn't offer him the job. So he was mad and he left. He went to Berkeley and he built up an infrared group. Okay? So there, they began to work on the galactic center using mid-infrared spectroscopy. So in 1980, Reinhard joins the Towns group. He and I were Miller postdocs at Berkeley. And one day, Reinhard says to me, I think I'm moving to infrared astronomy. And I said, why are you doing that? And he says, well, I don't know. And I said, well, if you don't know, I'm certainly not doing that. So I said, you go do that, and I'm going to focus on interferometry at shorter wavelengths. So by then, he begins to work on the galactic center, and after 10 years, he begins to work on the orbit. Reinhard used to tell me there's only 2 sources in the sky: galactic center and Orion. Everything else is useless. So he was very focused, laser focused on the galactic center, right? So in very short term, he was able to figure out the orbit, and gravity experiments that are very fancy now are doing excellent work. But actually, the experiment that won the Nobel Prize was done back in the 1990s, in 2000. And again, it takes 50 years of laser and interferometry research to be able to get to this point. So, okay, I didn't work on that either. I worked on imaging instead. To summarize, so Nobel Prize winning work is always defined by precision. Okay, so if you are thinking, what is it that makes a Nobel Prize winning work? The answer is that you actually have to have very high accuracy in order to get to fundamental physics. Typically, you should aim for a factor of 100, a factor of 1,000 improvement in some dimension. Okay, then you can find a very important phenomenon, and these will typically lead to important technology, important new technology, and that will drive the discovery, right? And you'll note that sometimes Nobel Prize winners also have more Nobel Prize winning work coming afterwards from their students, postdocs, and you have to ask, why is that? Is it because the advisor is so brilliant that anything underneath will become also brilliant? Or is it that very excited young people will gather around these centers of excellence, right? Of course, it's a combination of the effects. And for really good work, actually the problem will have multiple prize-winning work to follow. So pay attention to that when you're picking your problems. Now, finally, gravity can be seen, okay? So, can you see it? So we want to take a picture of the black hole. Reason is to get to the event horizon, get as close to the black hole as possible to test physics, right? So, we looked at the sky and we knew that there were only a couple of examples. The M87 was a very good target. The event horizon size is on the order of about 100 AU, we think. But it's quite far. It's 53 million light years away. That Schwarzschild radius is 10 microarc seconds, right? So compared to Reinhard Genzel's experiment, this has to go another factor of 1,000, okay? So the sun and the moon is 30 minutes, arc minutes. The black hole is 5 times 10 to the minus 9, the size scale of the moon. Okay, it's a very precise experiment, and as Beijing already showed you, gravity will affect space-time, theory suggests that space-time itself will be distorted by that mass, and that's very necessary in order to explain why light will also be bent, right? Because classically, light does not have mass, will not respond to gravity. However, since space-time itself is distorted, light has no choice but to follow that distortion. And it is following that distortion that the light winds up falling into the black hole if it gets too close. Okay? So in this case, in physics, normally material dielectric is used to bend light, the difference in dielectric properties. Here we're talking about the geometry itself changing the direction of the light. So if you're looking from the right here towards the black hole, the light which is getting too close to the black hole's center there, within 5 times the Schwarzschild radius, that light cannot avoid being pulled in, and because of that, it is missing in the direction that we're looking. And therefore, you cast a shadow, which is the size 5 times the Schwarzschild radius. So, in the center of our galaxy, for example, for a long time, we realized that there's something very interesting going on. On the left side here is a radio image at a wavelength of about 90 centimeters. And you see a splash of stuff going on across the plane of the galaxy, okay, which is going like this. And you see some ring-like features. Every one of those rings is a supernova remnant. Actually, the explosion of the supernova drives the material out and forms a shell. And you see many shells like that, right? And in the very middle of the galactic center, there's also a splash of light. Turns out that's also a supernova splash, okay? But if you look closer in the middle, you'll see that there's a spiral-like pattern. And if you look closer yet, there's a point-like thing which shows up. And this is the one that Freddo thought, Lugonian thought, might be a black hole. So directly imaging this black hole, we thought, because seeing is believing, we take this example, take that size scale, and we knew that we have to build an instrument with a precision of 10 to the minus 10. Interferometry was the technique that we wanted to use, and we want to try to do this at some millimeter wavelength. So the question is why? Okay? The reason is that, of course, things that are further away will look smaller. Even if they're very big, they will look very small. We need a telescope which is defined by diffraction. Diffraction just says that the resolution, the ability to resolve things, depends on how many wavelengths you can squeeze into a device. Okay? So if your device is size D, how many wavelengths can you squeeze into it? So, in that case, a short wavelength, sub-millimeter, 1 millimeter, will require a size of 10,000 kilometers in order to achieve 20 microarc seconds. So what's 10,000 kilometers? Well, that's the size of the Earth. So the experiment said we have to build a telescope the size of the Earth, work at 1 millimeter. So this we do with 8 telescopes. In 2017, Taiwan is partner on 3 of those 8 telescopes, and we deployed our instruments in order to do this experiment. Very long interferometer, very long baseline interferometer, such an elegant term, and simulate a very large telescope, the size of the Earth. You have to link the telescope in order to synchronize the light coming in. We use atomic clock to record when the signal is coming in. Then you have to correct the position of those telescopes at 1/20th of a wavelength, 40 micron, over a distance of 10,000 kilometers, okay? So it's a very precise experiment, right? You need to know exactly where you are, even though you're separated by such a long distance. So we need to correct many things, measure the distances, track the arrival, correct for the atmosphere, compensate the electronics, compensate the telescopes that are different in many cases, and correct for the fact that the mirror is actually the telescope that we're building is only 8 pieces, right? It's sort of like if I took a mirror and I threw it on the ground and broke into a zillion pieces, and I say, okay, now pick up 8 pieces and make me an image. That sounds like a tall order, right? How do you restore the image with only 8 little pieces? The answer is you have to know what you're doing. You have to know exactly where those telescope pieces are at all times, relative to each other, and then you have to correct for the defects, the fact that you have broken the mirror. Okay? So, of course, this technique also won a Nobel Prize for Ryan Hewish. It's called aperture synthesis, which is image reconstruction. Okay. The other source, this one, which we're looking at in M87, is a very interesting source. In the middle here is actually the Hubble image of the M87. And if you look at it, you see a tiny little jet of stuff coming out. Okay? It turns out that these jets are well known in radio because we've seen them a lot in radio. In the same case, when you look at it in the radio, actually the jet is much, much bigger than the galaxy. It goes further out and it blows up into this bubble of relativistic plasma. Okay? And if you look very closely at that jet with higher and higher resolution, now all the way to 43 gigahertz, we see at 10 milliarc second, it is a jet very well formed, focused in the middle. And theory suggests what is in there is likely a black hole. Now, why would we think that to begin with? It's because the amount of energy you need to push a jet to such great distances in the galaxy, it's hard to imagine what could be the energy source. Okay? In theory, and we also suggest, it's actually because we've extracted the energy of collapse, energy of matter, almost the full E equals mc squared out when you are actually close to the horizon of the black hole, because you've exchanged all of that gravitational energy now into kinetic energy, or radiation energy of some form, right? So this experiment, we want to try, already have the imaging, which suggests that the black hole might be the source of the jet. We're expecting to look for the shadow around that black hole. We calculate the size to be about 20 to 40 microarc seconds. And the reason we think that is because in the Hubble, you can actually track the stars moving around the center of M87, much like the experiment for Genzo, where you saw the S2 star going around Sagittarius star. Here, we're looking at all that stars around the center of that galaxy, and we can track the rotation curve and deduce the mass on the order of 3 to 6 times 10 to the 9 times size of the sun. Okay, and it tells you what the Schwarzschild radius would be. There's a factor of 2 uncertainty because the actual measurement of that rotation depends on the technique. One is dependent on stellar motion, the other one is dependent on the gas around those stars. So there's some uncertainty. Okay, so direct imaging, what we are looking for doing is to take that image where we have that little dot with an angular resolution of 1/10 of an arc second. Now we want to improve by a factor of 10 to the 5 and actually look for the material swirling in towards the black hole. Okay? So that's the experiment to try to improve by a factor of 10 to the 5. So of course, we calculate the theory as to what it might look like. Here are some calculations. On the top row is where we have only optically thin flow and spherical geometry, right? Saying that the collapse is uniform all over, spherical, and you see a black hole shadow because of the absence of light if it's not rotating. However, if it's rotating, then it might get a little bit squished. And then, if the material that's falling in is actually in a disk rather than spherical, one might expect that it would be a disk because we think that there's angular momentum always there, then you will see a flattened disk, and that disk might cover that black hole on the bottom, and then allow you to see about half the black hole, and then one side of the disk should be brighter than the other side because of that Doppler boosting, right? The motion towards us versus away from us will boost the intensity of one side versus the other. So that's the signature, and then we do the calculation, make the interferometer, what should we expect? So roughly we think that you see something like on the right. Okay? This is calculated for the right size of supermassive black hole, and then looking at that and see what the experiment might predict. So we deploy our teams. From Taiwan, we have staff who went to various observatories, various organizations also post their people to the telescope. We do this experiment, and the experiment works like this. As the source goes over the Earth, various telescopes begin to come into play. So for example, at this point, you can see the large millimeter telescope in Mexico, ALMA in Chile, and Pico Valletta in Europe. In red on top, actually you see that GLT at that moment in 2017 was not yet in play. NOEMA was not yet in play because it wasn't yet working. But as the shadow goes towards the left, it begins to pick up the Hawaiian telescope, JCMT, as well as SMA, which Taiwan's are partners on. So the way the experiment works is that as the Earth rotates, we begin to gather data on these baselines. So this is sort of like the Earth's mirror that we're building. And you can see that as the data comes in, that mirror starts to be filled out by data. and there are tracks because the track corresponds to the fact how long we can actually see the source at each site. And then you can see the image, which starts out to be not so good, will improve steadily as you get more and more data, okay? First, kind of lousy, then kind of clumpy, and then eventually the ring emerges. So synthesis, active synthesis is building up this mirror using Earth's rotation as the technique. And then visibility, as you can see, has to do with the fact that the actual source has been sampled rather lousily by these 8 telescopes, okay? Now, we write down this equation, you say, oh, well, that's simple, right? Just divide out by the sampling. Then you get back the image. Why don't you just divide by the sampling, since you know the sampling so well? Well, the problem is the sampling function has a lot of zeros. So you divide it, you're going to get a lot of very strong infinity points, right? So just dividing doesn't work. Actually, we have to use various techniques in order to restore the image. One of these techniques we use is called phase referencing. And this is to utilize the fact that ALMA itself has a large collecting area. So we can use that to correct for the fluctuation of other telescope sites. Because we have several telescope sites all measured at the same time, we can use that redundancy information to correct for the defect in each telescope. So originally, the response function might be kind of crummy, but after this phase referencing, you'll see that the response now becomes very good with the errors suppressed, and now you can make a nice image, okay? So that's called phase referencing. And then there are other things that we use, self-calibration and all these other things that need. But what you get afterwards, when you get the properly assembled map, it looks like this. But at the end, this is the answer. Pretty amazing, right? Almost like magic. Is it believable? Well, if you're an interferometer person, of course you know that this is believable because what you see on the left side is actually the response of the instrument. The response has defects which you correct for it. But we don't trust ourselves. We actually have 4 different teams actually doing this, and you can see that 4 teams using different methods of analyzing the data. And the top row came down with that answer. And compared to the model, you can see clearly it's not a uniform ring. Clearly it's not a disk. Clearly it's not a double. Most consistent with a crescent, right? Sort of. More or less, all the methods of modeling shows roughly that picture. So variability is something we looked at. We had data over 3 days, and you can see that actually the picture is fairly consistent on the bottom here. So we say the small scale structures looks pretty stable, the large scale is slightly different, and that's good because the large scale means the longer baseline actually is probing the event horizon. So we think that there are detail to be teased out of this experiment. How do we predict our proposal to begin with versus what we actually measure? And here you see that the proposal suggested that the image will look like this thing on the left. On the right is what we actually measure. So the prediction is actually pretty good, right? Except for the fact that the ring is flipped. Why is that? It's because we did not know whether the ring, the black hole, will be spinning toward us or against us. Okay? It's that flipping of the direction that determines the up versus the bottom color boosting of the light. So again, what does the image say? It's a black hole. But from that, the size scale of that black hole, that ring diameter, 42 micro-arc second, allow us to calculate the Schwarzschild radius. And from that, you calculate how much mass is in the middle. The answer was 6.5 billion solar mass. And you can see that was one of the answers from the optical Hubble measurements. Okay? So it turns out the stellar motion was most consistent with this kind of measurement. From the brightness of the ring itself, actually we can deduce things like density of the plasma, how much the magnetic field might be, and how much accretion might be going on into the black hole. The ring asymmetry that we see brighter on the bottom side is consistent with rotation. That is, you see the boosting of the light from the side that's coming towards you. The disk has to be tipped. If the disk is face on, definitely you cannot see the rotation motion, right? So it has to be tipped. And the tipping motion makes it perpendicular to the jet, which is coming out, and the spin of the black hole is pointed away from the Earth, as it turns out. Now, it's important to note that the spin of the black hole is forced by, will drag all the stuff around it. to enforce that motion. Okay, why is that? Because the thing that's closest to the black hole is responding to that gravity. And that gravity is turning, it will drag all that material closest into spinning in the same direction. So it doesn't matter whether the outside part, which is the blue thing on the outside, is spinning one way or the other. The inner part will be enforced by the spin of the black hole. So in the two left case, the spin forces the spin of the material, the accreting material, very close in to be always pointed in that direction, while the outside might be different, from top to bottom. The spin will be forced by the black hole so that its color is brighter. Had the spin been the other direction, then the color would have been boosted on the top part. And that is how we can tell the spin direction of the black hole. Now, theory, of course, is actually much more detailed, right? On the left side here is just the actual simulation of the material going in. On the right side is actually when you tip that accretion material, you will see that depending on the orientation of the accreting matter, you will see boosting on one side or face on where it's uniformly bright, right? So the theory tells us that you can calculate these things and expect to see that from theory. The theory, of course, is much more detailed. On the right here, depending on the light path, how many times light goes around the center, exact detail of the general relativity, you will predict a very different picture on the right. But in this experiment, because the resolution is so poor, actually all theory are acceptable, most theory are acceptable. We see basically this when we combine with the instrument's resolution. So now, I already talked about the M87 results, which was in that case, right? So now I want to talk about the actual picture in the galactic center. Okay? The galactic center on the left here, you can see, actually it's quite dark in the sky. You can see that very beautiful Milky Way. But you can also see that the Milky Way has a lot of dust in it, which means that in the optical, you cannot penetrate. Right? In the radio, as I showed before, you can penetrate and see succeedingly higher and higher resolution what the stuff in the middle ought to be like. Okay? So this experiment is to try to resolve the galactic center. The experiment was actually executed at the same time as M87, but the galactic center is 2,000 times closer. It's also 2,000 times less massive, so we believe we should be able to see it, right? Because M over R turns out to be about the same. Now, that S2 star got within 100 AU of the galactic center. What we want to do is to go 1,000 times closer to take a picture of the event horizon itself. Right? What will the picture look like? This is the experiment where we're looking in through the dust, going through, see the central part, the supernova. As you go in, you can see a ring, and you start to see the spiral. And as you resolve all the stuff, a little dot appears, and you magnify, and look, it's another donut. Okay, so the point is, when we built a large enough telescope with enough power of resolution, 1,000 times better than the experiment that did the orbital motion, we now can actually see what is happening around the black hole. So that fact that we get a donut is very important, right? This monster, relatively close to us, and 8 kiloparsec away, this is the second black hole that we successfully imaged. The donut, again, is a ring-like shape. This confirmation that the ring is an identifiable feature for a black hole. Why is that important? It tells you, at that stage, close to the black hole, gravity wins over all other processes. Right? Only matter at that point now is gravity. All the other sources of activity and energy are resolved out, are not important, and now the characteristic signature we expect going forward will always be a donut. So seeing is believing. This is the first visual evidence that this object in the middle is really looking like a black hole. Previous to that, we know that there's a lot of matter, but we don't know what it looks like. And the size scale is very small, 100 millionth of a degree, 50 microarc second. What is that size scale? This is the size scale of a donut. on the surface of the moon. Okay? If you want to see a donut on the moon, whether it's sprinkles or chocolate covered, you need that resolution. The two objects are different in terms of mass and size, so it's very important that such huge difference in size scales still is the same relative phenomenon. And the angular size scale is determined because of the distance and the mass, so that it just scales to be exactly the same. Okay? This is just a fortuitous thing. And then, of course, we can do the theory on the left, predicting all the possible way that rings should look like, reconstruct, and then compare to the observations. Now, there is some difficulty in the galactic center versus M87. The galactic center is a much smaller black hole. That means that it will actually be able to rotate on the time scale of hours and minutes. Okay, what does that mean? It means that while we're doing the experiment, the black hole is actually rotating. And that's why it took us a long time to actually make this picture, because we had to figure out how to model the data as the data is changing constantly in order to get that final image. Here's our team in Taiwan, which worked on this experiment. Many people worked on this. And some summary is that, of course, the experiment, again, depends on resolution. Okay? Gravitational wave, of course, is a coalescence process, things that are colliding together, then releasing the gravitational wave, right? The optical infrared interferometry that we're talking about in the event horizon dynamics problem, that is actually feeling that gravity, right? And then, of course, test the GR effect. The first one also is testing the GR effect when you look at the tail end of that light as it swings out, after the gravitational wave is peaking out. That signature in there also carries the GR effect. So sub-millimeter, of course, we are directly imaging the event horizon and then testing the GR effect there. Next generation, of course, we are going to improve in sensitivity in all these areas, and will play a strong role, I expect, in Asia. So what is the history of seeing the black hole? Okay, so as I mentioned, Fred Lowe very early on suggested that this could be a black hole. In 1991, Typhoon Lee suggested that we should regrow the astronomy in Taiwan. And a couple of years later, we established a preparatory office. Fred Lowe became director. We complete the SMA. We start the VLBI group. We built the amoeba. We completed our project, its participation in ALMA. And then we recovered part of that ALMA project as the Greenland telescope. In the meantime, we are participating in the Event Horizon experiment. And then actually now we are on the way to make the next image of the black hole. Okay? So here I am sitting on the right, influenced by Charlie Towns. This is very early days in this meeting. And of course, what is he telling us? You should go study the galactic center. That's what he told us. So what can I tell you and cannot tell you? Well, the image is being improved as we speak. Okay? The next epoch, 2018, actually has the GLT data in there. The map is sharper, but I'm not allowed to reveal to you. Well, okay, if you don't say anything, I'll tell you that the image is better, and we see hints of rotation, but it still need time to confirm. Okay. Polarization data we're analyzing, we're also studying active galactic nuclei. Experiments in 21 and 22 also has taken place. We had a gap of 2 years because of the pandemic, but now we have resumed operation. And the backstory actually is that this took Taiwan also 30 years to develop. So now I'll tell you a little bit in the remaining half hour about the project that we're pushing to build the largest telescope ever. And that's the Greenland telescope, leveraging the submillimeter array and the ALMA and JCMT in order to form this triangle, which is the size of the Earth. Now, the previous experiment already is the size of the Earth. What is the difference here? The difference here is that we will push the wavelength down. Lambda over d, we will achieve another factor of 3 improvement in order to sharpen this image of the Event Horizon Telescope image that you've seen so far. Okay? So we picked Greenland because it's actually a very high site. It has 3,000 meters in elevation, very cold. Mean temperature in the winter is minus 60 degrees. Okay? So our objective is to place this telescope there in Greenland, as you see here. The purpose of that project actually is to recover our investment in ALMA Taiwan. So we obtained the prototype antenna that was built by North America, and we retrofitted it in order to make a telescope which will work in the Arctic region. And then this leveraged the ALMA collecting area in order to provide Taiwan with a project which actually has its own special property and extend the ALMA capability, right? So we're trying to expand what ALMA can do in Taiwan with this particular project. It started in about 2009. So the telescope needs to be transported to Greenland because it's actually only a couple of months a year that the seaport near Greenland is not frozen, that you can actually get a boat in. And we had to transport our telescope there. We start from the Norfolk Naval Base in Norfolk, Virginia, and we sail into Greenland on top here. We can also fly in, but the plane is too small to carry the big parts, so we actually have to put it on a boat. Now, on the left side, you'll actually see me staying on this tugboat, watching them moving the telescope onto this big boat. And the reason is that even though the telescope was 3 miles from the boat that was anchored at the naval base, we could not get in because the naval base front door is locked to prevent, it's barrier to prevent large things to come in, right? This is the times that we're dealing with today because of terrorist possibility, you could not get in through the front. So I actually had to hire a tugboat. And a tugboat cost me $50,000 to go 3 miles. So I was really crazy, mad that I had to pay $50,000. So I was on the boat to make sure they didn't drop it. Of course, if they drop it, what would I do, right? So it was quite exciting to get this onto that boat. So shortly there, in 2016, we arrived on site and we began to construct and put the telescope back together. In 2017, it was completed. Now, it took a year to do because winter is not workable when you're in Greenland because it's in total darkness for a number of months and the temperature is quite low, even at the seashores, okay? So we are actually working at the Thule Air Force Base, a US Air Force Base, where we assembled this telescope. And actually this shows the strong support from the industry in Taiwan. Actually, these side cabins were constructed in Taiwan and mounted by this team coming from the industry side to help us do this and to assemble the telescope. Without their support, I think we cannot do these things. And this side cabin contains the electronics because we're in a very cold environment. We want to protect the electronics, okay? But work very fast, okay? 2017, we finished. 2018, we already started the experiment. Okay, so the team actually worked very efficiently. If you can imagine to take something like this, mechanically assemble together, get all the electronics connected up together, get them all working, calibrated, and receive the data, right? So actually, it was a very exciting time for us. For our experiment, things are actually quite difficult. Here, we actually showed that in the subsequent years, we improved the surface of the telescope. On the right and the left here is actually the error pattern on the telescope surface. The left side has a saddle pattern. It turns out that when we picked up the telescope, you know, to mount the dish onto the telescope, that lifting point distorted the surface. Okay? And we could not tell until afterwards when we were on the telescope that we can measure this by photogrammetry, where we actually photograph the surface in order to measure this. And then somebody has to go up and actually adjust every panel until we finally get a surface that's much, much better on the right side. So there's a lot of hard work involved in doing this kind of work. And then, of course, we also went through this period where we had the pandemic. In the pandemic, we couldn't actually put our people in Greenland to do the experiment. So we actually established a remote operation from our offices in Taipei. Here we are controlling the instrument by installing cameras and remotely observing all the instrumentation. And then we have one technician on site which works at the Air Force Base, comes and checks to make sure that we haven't done anything terrible. And that's Locutus, one of our staff, who actually was the person in charge of setting up all the computing system so that we can actually remotely operate. So the pandemic actually was very good in the sense that it made it impossible for us to be there, but it also makes sure that we can do this remotely. Because when we get to harsh conditions, actually it's quite hard. So the backstory of this is that when the pandemic hit, I was just coming back from Asia. Okay, this is the beginning of 2020. And I was in Asia about February, and already noticing there's something going on. How do I know? I was actually in Thailand, and came down for breakfast one morning, and I noticed that everybody had masks on. In particular, even children had masks on. What has happened? Actually, most of the tourists in Thailand were from China. So they already have some news that day. Something is happening. And very soon after that, the news spread that, something has to be, we have to be very careful. In fact, when I came back from Thailand, everybody in the office says, get out. We don't want you here. Go stay in a hotel. But after that, I returned to the US, and things began to really mushroom in the US, right? This was about March now. And many cases began to happen in the US. I had 2 people in Greenland at that point. I told them, pack and get out. One person was en route, was in New York, about to get on the plane to go to Greenland. I said, turn around and go back to Taiwan. Why? At that point, we don't know what will happen, right? If you get sick, there's nothing we can do. So it's just too dangerous to do experiments. So science is important, but life is much more important. I pull my staff out. In Hawaii, I also pull my staff out to stop them from going to the telescope. We shut down. So while we're doing these kind of research, we are always affected by whatever is going on, right? So we have to be very careful to preserve, of course, everybody's health is most important, and then we work around it. Now, eventually we'll go to the summit, and here is a picture of the summit at 3,000 meters, here in the center of Greenland. This is where we're going, and in the summertime, you can see that people actually live in tents at -20, because the housing, there's not enough housing on top. Okay? The only housing is actually in this little building on the left over here. Under the dome, you can only have about 6 people stay there. So in the summertime, about 50 people are working on site. They're all living in tents. Now, is that okay? Yeah, it's okay, Well, bathroom is special. You have to think about what to do about bathroom on the ice sheet, because there isn't none. The problem was, a few years ago, a bear showed up. Now, a polar bear should be at the coast. How did a bear go from the coast all the way to the summit? We don't know. They navigate well. And they showed up. Once they show up, they wouldn't leave, right? Because they know where the food is now. So that became very dangerous for the people on site. So that's also part of the living problem. On the Air Force Base, of course, it's actually much better. The Air Force Base is well facilitated. This is an Air Force Base which is sort of the northernmost Air Force Base in the United States. In the old days, in the Cold War days, it is the last point for to look over the horizon at the Soviet Union. Okay, today, for a long time now, actually the base is not so active, but now it seems to be active again. But on the base, there's a few hundred people, and therefore, there's even bowling alleys and various things to entertain yourself. These will be the sleeping quarters that we use. And of course, one of the things important to be astronomer is that you have to be a good cook. Okay, so here are our team cooking our various international cuisine. All of them turns out to be pretty good. That's a requirement if you want to join our team. You have to have good cooking skills. And then, of course, sometimes you would like to do something else. Ready? There we go. Not very far, right? Okay, we'll let the camera pan around. Okay, there's a telescope in the back, and this tells you that even in the sea level, the snow is enough to actually cover quite a large height that we have to dig ourselves out every winter when we get to the telescope. And then, of course, there are things like polar bear, as you can see over here, and occasionally you see these moxoxen, which is quite interesting features. And then, of course, sometimes people have more interesting things to entertain themselves besides eating. They tell me it's cleaning fluids. That cleaning fluid on the right looks interesting. They assured me this was after hours and that they're all adults. Okay, and then of course, once you establish the telescope, VIPs begin to show up, right? So on the left top here is Neil deGrasse, as we know, he's Carl Sagan in the 21st century, and he heard about us somehow, and he came out to take a look. And the Prime Minister of Denmark showed up in 2018, in October, on a visit to the Greenland. Greenland used to be a former property of Denmark, so they are still overlooking Denmark as a supplier of funds and defense and so on. So sometimes Denmark people would show up, and on the bottom right is the Secretary of U.S. Air Force. She's also the Smithsonian Institution board member in 2019 visiting us. And that's Satoshi Matsushita, who is now PI of the GLT project. But most excited people were by this guy, because he was Jaime Lannister of the Game of Thrones. So he was the most important celebrity that actually visited us at that project. So has the GLT contributed? So in 2018, as soon as we came on, we actually participated in this experiment. Okay? And this experiment was able to detect and I have to say, this is actually doesn't have the GLT in it. This is the pre-experiment in 2018 when we didn't have the frequency up and running yet. Okay? But in fact, we had a little bit of data in there. And the experiment actually shows, even though the Greenland telescope was not working perfectly, that it improved the resolution of this experiment. Okay? So this was the ring that was seen in the Event Horizon Telescope experiment. And this is the experiment that's seen in the experiment that we did at a lower frequency. Okay? What happened at the lower frequency is that we actually now pick up the jet. And the jet can be seen to be falling right on top of the black hole in this ring, right? So the jet is clearly originating from the vicinity immediately around the black hole. And furthermore, when we measure the black hole size, the donut turned out to be a little bit fatter. And this worried us a lot as to whether our calibration was correct or not. But after we did the calibration very carefully, we understood what this is actually seeing. It's actually seeing stuff that's falling into this black hole on the outside. And as a result, because of the sensitivity of that lower frequency, we actually picked up more of the material that's falling in, the accretion component. On the right side is actually the sort of the last orbit of light around the black hole. On this side is actually an additional accreting matter onto the black hole. Okay, so going forward, what is it that we're after? In the middle is the current picture that's published, the donut with 9 pixels. Okay? The next experiment, which we'll show you, but I cannot show you the picture yet, actually improves by having 25 times pixel. Okay? And then when we get to the top of the mountain, which is what we're aiming to do at the moment, we'll have 225 pixels, right? So you can see that with that many pixels, that ring will be better resolved, and we'll be able to test whether the first ring of light is a complete ring, whether it just goes around once, twice before it goes in, and then the detail of that ring will carry more precise information on the GR effects. At the same time, because at higher resolution, we will be able to detect more distance or smaller black hole, such as in Andromeda. So a black hole in Andromeda will now also be resolvable into a ring. So we were expecting to see 5 or 6 more cases when we get to the top of the mountain in order to do this experiment. So what is the story behind doing excellent work? Okay? As I said, the key is to drive to precision. Okay? You have to develop new technology. If you don't have new technology, you just cannot get things done. So you have to improve things by a factor of 1,000. We ask, can Taiwan work at the frontier? The answer is yes. How do you find the right problem? Actually, you have to find the right people, right? It's not about the problem, it's about people. You have to find the right people. Well, how do you find the right people? You actually have to work at the frontier, because anybody who's good will want to work at the frontier. So you have to aim at the frontier, find the right people. Is that enough? No. Actually, the most important part, in order to get enough resources, is you need a godfather or a godmother. Okay? We all know this, right? A godfather or godmother will allow us to overcome the problems that we cannot solve ourselves, they are placed at the right problem so that they can see the possibilities and they can find the solution, which we ourselves on the ground is working very hard to get to, but we cannot overcome without our godfathers, okay, or godmothers. How to choose the right direction. That's very important research, right? Recommendation to you is always go new. Do not go through the same ground again. Find a new path that hasn't been done. How do you make sure that you succeed? The most important quality you have to cultivate is being persistent. You have to keep doing it, and you cannot give up. And that is very important. And then, what is our guiding principle for this generation? Our guiding principle is that the future will always be better. Okay? So we have to believe the future will always be better, and the people who will be better are always behind us. Okay? So that is why we push forward. So in Taiwan, the strategy involved the radial path and the optical path, and we did a number of projects, to build up what we need in terms of manpower, in terms of technology, in terms of the expertise that allows us to be prepared. Okay? So we went through and built the submillimeter. Why did we build the submillimeter array, join the submillimeter array? Was because we were very conscious of not working on projects that other people are already working on. Why? Because by the time we are ready, those people who are working on those projects have already skimmed the green, right? Have already done the experiment by the time we get there. So we needed to jump ahead to an experiment or project where things have not been done yet. And that gave us time to prepare. Okay? So working at the frontier is a little scary, but you cannot do it by yourself. You need help. We have partners which guarantee that we will not fail, right? And after that, we built the amoeba. This was an experiment where we did it ourselves. Why did we do it ourselves instead of having a partner this time? Was to make sure that we can integrate the system, design to production from end to end. Okay, this is an experiment together with Taiwan University, funded by NSC, and involved many industry and electrical engineering departments in the country in order to build this instrument. But the most important part was to get to the point where we can actually do things completely on our own. Then we joined the much bigger project, which is ALMA. Why? Because we knew that it would be much more powerful than the submillimeter array, and again, it would be a frontier instrument. So we were pushing to join that project. In 2013, we completed our contributions and started to work. And then we joined James Webb Maxwell Telescope as part of the East Asian Observatory. This effort was driven by the fact that we realized that in Asia, we should be working together just like in Europe. Okay? Europe is extremely strong. They are now better than North America. The reason, there are 16 countries working together. That is why their projects are ahead while others are behind. So we want to be able to achieve that in Asia by working together as well. But this turns out to be also an extremely important telescope for the VLBI experiment. Now in 2017, we deployed the Greenland telescope successfully, and you can see that we're definitely in the North Pole. As you can see, the star tracks all going around overhead. At the same time, we also built up our infrastructure in terms of how we do devices, and this was a very important superconducting junction device laboratory, which is the heart of the instrument that we're working on at all times, and the ability to build these things actually took us years, and now we have a very fine facility that allows us to produce all sorts of things, and now this lab is also now working on quantum computing. So in Taiwan, our astronomy is now quite global. On the left, of course, is where we are in Taiwan, and then from below you can see the submillimeter array and amoeba in Hawaii. TAOS 2 is actually now deployed in Mexico. ALMA is in Chile, and Greenland telescope is in the North Pole. So the sun never sets on Taiwanese astronomy. So for those of you who are interested in astronomy in Taiwan, you should feel that this is now a very viable field for your future. And of course, science has to be led from the top. Here are our godfathers. As you see, Wu Dayu is there. He was the person who said that you can actually start up again in astronomy. And he was the person who says that the institute can be started within the academic synagogue. And there is Typhoon Lee, who was the first person proposed that we should do this, and then he's supported by Wu Dayu. And then after that, Yuan Li was the next academy president, working with Fred Lowe here. This was in Hawaii when we dedicated the submillimeter array. And of course, Chi Wei is there when we dedicated the amoeba, and then there's the gene cell, of course, on the day that we announced the black hole results. In the middle, actually, is the person, Frank Shu, who suggested that how we should bring up the institute in the Academy Sinica, and Wu Maguan on the right, who was the NSC minister who approved the Arnold project, right? So as you can see, we cannot do things without the help from the very top. And of course, good science takes time, right? And here you can see one of our chief scientists at the time, a young man, Saming Tan, who was in charge of our receiver development, and he gave up something to become successful at the end, right? He lost a lot of his hair. And on the left, you can see our godfathers. There's Wu Dayu, Yuan Li, and Liu Zhahang in the back checking on our equipment. So science is a product of teamwork. We would like our students to join in our progress across the ice sheet. Now, why is that? It's because going to the summit is actually quite difficult. There's ice crevasses that occurs on the ground every winter. And for that, we actually use satellite images to map where the crevasses are. And we try to go around the crevasses. But still, you're worried about small crevasses that are lost in the imaging of the satellites. So we actually have a ground scanning radar on a small tractor that's in front scanning to make sure we don't fall into a hole. But it occurs to me that the tractor itself is also quite expensive. So I thought I should have a dog team in the front manned by students. So if the students fall in, well, we just recruit another student, right? So please join our project. We hope to go forward in the next 2 years onto the summit. And the journey can go anywhere. For me, it began with the dominant seminar as a freshman, so you never know. So my recommendation, make sure you eat lots of donuts. I'll stop there.
Okay, when I began my grad student career at UCLA, we had 7 seminars every Friday afternoon right now. And each of these graduate students has to take a turn to go out there and buy donuts. And the other graduate student will order. I want chocolate, I want vanilla, and I say, I want hot and sour. We'll make it go so hot. Okay. Okay, that's why I didn't know. But you know, for Asian people, they eat donuts and coffee to have heartburn. That's why I didn't go into astronomy.
That's why we have to train hard.
Okay, those dogs are really cute. 好，有没有问题要问那个？OK， 好，后面的同学，我们那个麦克风给后面同学。
Hello, Professor. Thank you for your amazing sharing. And I have 2 questions to ask. The first one is about the gravitational wave. I wonder that if there are 2 events like the black hole collapse together, or the black hole and the pulsar collapse together, if there have more than 1 event on the near or the same position, can we distinguish different events, maybe by theoretical model, compare with theoretical model, or compare with other message like gamma ray or other maybe. I wonder if we can distinguish maybe more than 1 event, or there is or the probability is too low that we never read like that. The second question I want to ask. Okay, thank you.
Okay, so the first question is, as far as we know, there's only 1 event. It's actually the actual coalescence of the 2 objects that gives this burst of gravitational wave. So they don't bounce or do something else, as far as we know. And how we know is due to calculations. So you compare with theory, and from the ring, you can actually deduce what the 2 mass objects look like, because it gives you the orbital period and the strength of the coalescence. And then the actual objects themselves, as I showed, if you can detect the afterglow from the objects, which is radiated afterwards, you can actually calculate what the initial event is also and identify some additional property. So multi-wavelength tracking of the afterward event plus the initial chirp of the gravitational wave for 10 to the 7 together builds the model of what will be.
好，大家了解他的问题吗？就是你知道不了是两个黑洞或者什么？刚刚我讲的是2017年有一个0817的那个是两个 neutron stars coalesce， 所以完全有其他 radiation 出来就不是黑洞。好，要不其他人有什么问题的？有没有 ？OK， 这边。
Was there a second question? She had a second question.
OK， 好，那你先问。再讲。好，再给他。
Thank you for your answer. And my second question is that if we have chance, it's about event horizon telescope. If we have chance to collect the data whole year, and maybe we can get the telescope that the radius is near 1 AU, or it's too difficult to reach. I wonder that.
Well, so the immediate measurement is always on the surface of the Earth. So the comparison of the two different telescopes is always the Earth. Even as you go around the orbit, it is still just those telescopes, right? So if you want to do a better experiment, you actually need to take a telescope and throw it over the side and let it drift away from you into the solar orbit. And then slowly that baseline will increase, and then you get a better, sharper picture. So people are thinking about doing that, how to get a telescope boosted into orbit and then to actually get it further and further away from us. So the best thing to do is to get the telescope in some sort of elliptical orbit so that we can change the distance to the telescope over time. Yes.
Okay.
Thank you for your impressive speech, and I have a question because you mentioned the scientists study the black hole by their gravitational force on the nearby stars. And I'm curious at the beginning how the scientists measure where the black hole is and decide which direction or whichever they need to focus on and observe the motion of stars.
So you're talking about the small ones, the early detection of black holes, or these two?
你在说的是银河中心那个还是 M87的？你应该说银河中心恒星在旁边绕，是不是？你说的是恒星在黑洞。
Does he show the picture about the motion of stars?
Oh yeah, okay. Well, that one, the galactic center one. So they were just taking pictures of the galactic center and trying to make a sharper and sharper picture. What they were trying to do in those early days was to see the stellar distribution around the black hole, right? They're trying to figure out how many stars are there. They were not really thinking about actually seeing something, right? But then somehow, during those epochs of experiment, they noticed one object was moving. Actually now we know that there are many objects that are moving, okay? So there are objects that have orbits that are 1,000 years. But this one happens to be 15 years, right? So you have to be lucky that a star have to be in the right place, and you have to have sharp eyes to actually pick it out. So you cannot throw away your data without looking at it very carefully. Usually something is very special that it's always been there, but you didn't notice, okay? So the person who notices the small effects is very important. So in this case, they noticed that some star is moving, and then they watched it, and they watched it. And only a few years before they realized immediately that it's an elliptical orbit. Okay? That was a very important part. That is the Nobel Prize winning part. That recognition of the small motion that actually, just like the Earth going around the sun, once you have an orbit, you can tell what is driving the motion, right? So they immediately, from that partial curve, they immediately determine how long is the orbit and what has to be dragging, pulling, and they figure out it's millions of solar masses. Because you immediately think that must be the galactic center. Then the test is, let's see if the orbit actually goes around the galactic center and whether it marks exactly the position where the mass should be for that orbit, right? So it's a very careful, elegant experiment.
I think the scientists in the 1930s, they noticed that the two strongest radio forces, one's the sun, the other one's the galactic center. And the German Air Force, taking advantage of that, they flew to bomb England. Instead of going directly over to England, they flew to the place where the galactic center is and turned around, so that strong radiation is just totally blind the British radar. They knew that there's something interesting during the 40s, right?
I didn't know that, yeah. Those clever guys.
但是我在讲什么？德国的空军要去炸英国的时候，因为英国的雷达很厉害，你一起飞他就知道，他不会直接飞英国，他会先飞过去以后绕过来，让银河中心在背后，因为银河中心是强烈的无线电波源，那无线电波源会整个让你的英国的雷达瞎眼掉，所以那个时候他们就知道银河中心很特别。
Okay. Okay, so thanks for your great talk, Professor, and I learned a lot from your talk. So I have one question, not very professional, but I'm still very curious about this, because we know gravitational waves is a torsion of space-time in a three-dimensional space. And in theory, the molecule, atoms, electron, both the basic particle, they are also a three-dimensional object, you can say so. So does that mean the gravitational wave, they also torsion atom, molecule, this kind of small particle from the three-dimensional part. Hey, if that's possible, would gravitational wave possibly affect the interaction between the molecule and the molecule in the disk cloud around the black hole or the neutron star?
So the gravitational wave is a very faint signal, right? It's extremely strong, probably right around the event horizon when you're colliding things. But at this moment, just to feel the effect of the gravitational wave is very weak. Now, I haven't done the calculations to see what is the effect on a molecule, but that measurement for the gravitational wave is extremely accurate, right? So I think you have to calculate whether the effect on the molecule can be seen or not. My guess is that it is many orders too faint effect on the molecules.
Yeah, because the gravitational wave around the black hole is very strong. It rises a meter level or even a kilometer level. So it may contortion the molecule or the atom in a very large scope.
Well, we need a lot of mass.
Yeah, so I mean a big mass.
Yeah.
Thank you.
Okay, you mean in the molecules which has a number of atoms, and if gravitational waves passing through the molecule, it may vary slightly, briefly, the space-time between atoms. So it may change the property of the molecules. I think that order should be way too small to be detected.
Well, it's a good thought. I should never say never, right? Everything that we thought never was possible then became possible. So you have to remember that one and keep checking. Yeah. So, generally you would say atomic things at one molecule at a time is difficult to do. But people are now working at one atom at a time, right? So there is very careful experiments where they are isolating the molecules and the atoms and the electrons very carefully, right? So maybe it's possible, but I haven't done the calculations, so I cannot say yes or no.
Okay,
So it's a good question.
I think gravitational wave doesn't know whether you are molecules only or inter object, right?
Distortion of the fabric, right? So it's you have to figure it out. What is the actual wavelength? I mean, it's very slow, right? As you see, the signal it's like sound wave, right? So even though the motion is at the speed of light, the gravitational wave is traveling to you at speed of light, but the wavelength of the structure is rather slow, right? So then can you affect things that are on very, very minute scale in a wave that's very, very slow? We don't know, right? Not easy to see that difference. It's like if you're in an ocean and a wave rolls in, it has a certain wavelength, right? But if you're very, very tiny, this huge wave coming through, the effect on a very, very tiny scale might not be noticeable.
So if the gravitational wave does affect the interaction between the molecule and the molecule, could we find a difference from the emission spectrum from dust cloud around this black hole?
I guess you're still wondering whether at the molecular scale, gravitational wave could show any effect at all. If that really worked, then a person would be.
So the Ganzo's experiment, right? They actually was watching the motion of the star. That's in a spectral line. Okay? That's an atomic line. And that they saw the gravitational pull of the black hole because it actually pulled the motion. In addition to the Newtonian effect, there was a GR effect on the motion. And we did measure that. That experiment did measure that. Right? So in that case, you can say that the molecule is actually affected. What you're asking is whether internally the molecule can see the difference or not. Well, that's difficult because the motion of the molecule at that moment is actually quite violent. Okay, so the smaller effects on top of this very large motion, we only see the broad shifting, not the internal ones.
Yeah, okay.
We can discuss this some more later. Yeah?
Yeah, but I think his question is similar to dark energy. Student asked once that dark energy is a repelling force. What's the scale that worked? Instead of the bigger ones, would it work among you and me? Yeah, I think that's the similar question.
The aspect is so small we can't see it, right?
Yeah.
Locally.
OK， 咱们一起看问题。好，后面那个，就是他跟他。
So thank you for the talk. You show the black hole image of the Superior A star, I mean the one in the center by the EHT. And I saw the image there are like 3 light spots, like 3 clouds in that image. And I'm wondering what caused that, like what the reason. I mean like one might be the Doppler boosting, what about the other 2?
Right, so I think in the galactic center, this science becomes more complicated because, as I mentioned, the star is actually, the black hole is actually rotating quite fast within minutes. So that the brightening may be a temporary thing within that ring, we think. Okay, so the image was not stable from minute to minute to minute. So the 3 lumps is sort of the average image. It was not 3 lumps at the same time all the time. So we still don't understand what those 3 lumps are. But the next experiments, what we're looking to do is to actually make movies so that we can actually see the structure evolving with time at time scales of minutes. So that's actually the next level experiment that we're planning to do. So at the moment, those 3 lumps may have some other effect besides just the Doppler boosting.
OK， 好，下一位。
Dear Professor, from the image of the black hole here, why the equation disk have so many hot spot bright area? Thank you.
Right. So I think one of the things that we want to do in the next experiment on top of the mountain, even in M87, which is a very stable image, the question is, what actually will the light be going in? Okay, so it turns out that you can calculate the light going in half an orbit and into the black hole, or with a little more angular momentum goes 1.5 time around and then go in, and then the next one is 1.5 time and go in, right? So it depends on the path of the light and how much angular momentum it had relative to the black hole. So when we get to the higher resolution, we will actually be able to tell that apart so that we can see whether each of the light is slightly different and the interaction between paths. And then, of course, you have to carefully remove the accretion part versus the last ring of light part. So right now, this image has too much physics, too much stuff packed into it. with the resolution that we have, which is why we are pushing to do the next experiment.
Yeah， 我想补充一下，因为黑洞中央的强大的重力场，那个光走的方式是不一样的，所以不像平常你看得到正面反而看不到，光会跑到另外一边去，背面反而是看得到的。你可以看《星际穿越》、星际效应的那个电影里面那个黑洞的长相就是那个样子。Yeah, okay. Paul, I'd like to add a comment to those. Paul was in a press conference, at M87, which year was that? 2017. M87 press conference, 那个记者会 with 6 places around the world simultaneously released that wonderful picture of this. There's so many people waiting in front of the computer because this will be great news. But afterwards, lots of people, non-scientists, they feel disappointed. They came to me, what's the importance of this? It looks just like a photo with bad focus. Do you get that kind of feedback?
Well, of course, you would like to see a much sharper picture, right? So it took a lot of effort, just to be able to see the donut. But eventually we'll see a better donut, see it more clearly, and that's what we aim for, and that's why we're pushing. Actually, in 2019, when the press conference happened, James L. was actually quite unhappy that I wasn't there, because at that moment I was actually in Denmark, there at the press conference. And the reason was that Denmark was a very important partner for us potentially in Greenland, so I was there to promote and push for their development there on that particular day. So I'm happy to say that since that time they have decided to become a partner in the project, so we become stronger going forward.
Yeah, I did see you there in Denmark at that press conference. OK， 好，叶老介绍的真的很精彩，我们就再次掌声鼓励，谢谢大家。